This is section 5-4, and we're not going to do much in this section. We just do the first few problems, 1 through 7. So let's look at something. From physics, we know that force is equal to ma, mass times acceleration. And we also know that on a spring, force is equal to kx, where k is the spring constant. And we also know that acceleration is the second derivative of position. So those are things that we know. So for a spring, the second derivative of position is going to equal kx. Okay, so now we have something that's weird. We have a barrier and a spring and a mass and another spring and a mass and another spring and a third mass and another spring and hooked on to some wall. And we have a K1 and we have a K2 and we have a K3 and we have a K4 for the stiffnesses of those springs. And we have a M1 and an M2 and an M3 for the masses. And we say, well, and we can put an M here. M second derivative is equal to kx. Okay, now that being the case, then we've got some x1, and we have some x2, and we have some x3. Okay, and all those things change with time. And then we can say, well, mass 1, x1 double prime is going to be minus k1 x1 plus k2 x2 minus x1. And then we can say that M2 x2 prime, double prime, is going to equal minus K3 x3 x2. Anyway, where was I? K2 x2 minus x1 plus K3 x3 minus x2. And then we can say that the third mass x3 triple prime, double prime, is going to be minus K3 x3 minus x2 minus K4 x3. Okay, so if we accept that that's a reasonable thing, we can say, well, that being the case, my x can be x1, x2, x3. And my mass can be M1, M2, M3. And my K could be written as minus K1 plus K2. K2, 0. K2, 0. Minus K2 plus K3. K3. K3 minus K3 plus K4. And except for the K's looking like R's, and the negative signs not looking the way they should, now we can write the system of differential equations as mx double prime is equal to kx. And we can expand this and say, well, gee, does it matter whether I have 4 springs or 5 or 6 or 7 or 8 or n? I could go and have a whole lot more and come up with the differential equations that have to be solved and put them in the form I'm in and do the same type of thing. Okay, well, that's nice. So now that we've done that, we say, well, I don't like the form mx double prime is equal to kx. I would rather have something that's in the form x double prime is equal to ax. That's what I'd rather have. So how am I going to do that? Well, if I go and do a inverse matrix of M and put it on both sides, I will find out that my A is going to be inverse M, K. Now, this inverse M is not 1 over M. That's not what it is. It's the inverse matrix. So if I take M inverse, I'm going to get the identity matrix. And if I take M inverse M, I'm going to get the identity matrix. So it has nothing to do with the minus sign meaning 1 over M. It has everything to do with it meaning the inverse of. Okay, so that's pretty cool. How do we come up with an M inverse? Okay, well, let's say I've got 1, 2, 3, 4. Oh, let's go with 1, 2, 0, 4. Make it easy. So let's say that's my M, and I want to find out what M inverse is. Well, I could go and take 1, 2. I could put it in my TI-89 calculator, and it's going to tell me what the inverse is. Okay. Or I could do something called elementary row operations. 1, 0, 0, 1. And elementary row operations are things that you did in 9th grade. You just didn't call them that. And so what we're going to do is we're going to do them on these things. And when on the left-hand side I get 1, 0, 0, 1, I get the identity matrix. Whatever I got on the other side, that's my inverse. Okay, so first thing I'm going to do is divide the second row by 4. And I'm going to get a 1, 2, 0, 1. 1, 0, 0, 1 quarter. Okay, and then I'm going to take the second row You take the second row, multiply it by 2, and subtract it from the first row. So I'm going to have 1, 0, 1, and then I multiply by 2, it's a half. It'd be minus 1/2, 0, 1, 0, 1/4. And now I know that the inverse matrix of 1, 0, 2, 4 is going to be 1 minus 1/2, 0, 1/4. And you say, well, thus says you. What makes you think that I think that? Okay, well, so we'll go and look and see. We'll see. We got 1, 2, 0, 4. And we multiply it by 1 minus 1/2, 0, 1/4. And what we're supposed to get is the identity matrix. So first row, first column gives me a 1. First row, second column gives me a 0. Second row, first column gives me a 0. Second row, second column gives me a 1. So I have the identity matrix, so that's good. Now it's supposed to work the other way too. 1 minus 1/2, 0, 1/4, and 1, 2, 0, 4. And I'm supposed to get the same thing. First row times the first column gives me 1. First row, second column gives me 0. Second row, first column gives me 0. Second row, second column gives me 1. So I get the identity matrix both ways, and that's how I would find an inverse matrix. And it doesn't matter, it can be a 3 by 3 or a 4 by 4 or 100 by 100. It's just that that's how it's going to work. Okay, well, so I have, if I could spell have, okay, so I have x double prime is equal to ax. Okay, so I have something that looks like that. If we say that the answer to this is in the form x of t is equal to v e to the alpha t, then x double prime of t has to be in the form alpha squared v e to the alpha t. Okay, so that being the case, so if alpha squared v e to the alpha t, that's going to have to equal a v e to the alpha t, where the v is my eigenvalues, and I can rewrite that as a v is equal to alpha squared v. So therefore, we use the therefore. X of t is going to equal v e to the alpha t. If this is the solution, so this is a solution of x double prime is equal to a of x. So that being the case, alpha squared has to equal my eigenvalues. I don't have a choice. Where lambda, the eigenvalue, is an eigenvalue of A, matrix A. And with V being the associated eigenvectors. Okay. So, in a mechanical system, typically, I like that word, the eigenvectors are negative and real, eigenvalues. The eigenvalues are negative and real. So alpha squared is equal to the eigenvalue, which is going to equal minus omega squared, which has to be less than 0, and alphas are going to equal plus or minus I omega, where omega is the angular velocity. So, that being the case, x of t will have answers in the form v e to the I omega t, which is going to be v times cosine omega t plus I sine omega's t. Okay, and I'll have a real part x1 of t v cosine omega t, and I'll have an imaginary part x2t, which is going to be, that's a v, the sine omega t. I'm still have to throw in constants of integration and other such nonsense when I get to my final answer. Okay, so that's the theory involved, and this theory very closely follows what you're going to have to experience in your partial differential equation classes, whereas if you don't follow the procedure exactly, you're never going to get the right answer. Okay, so we're going to look at number 2. You guys get to do the odd ones. I'll do the even ones. And I have m1 is equal to m2 is equal to 1. I have k1 is 1, k2 is 4, k3 is 1, okay, and I got my matrix M is going to be 1, 0, 0, 1. Okay, and my matrix K, and the book tells us how to get that, is going to be a minus 5, 4, 4, minus 5. And A is going to be M inverse K. Well, the identity matrix is its own inverse, so that's convenient. And so my A is going to be minus 5, 4, 4, minus 5. Okay, now I'm going to look for eigenvalues. So I got A minus I lambda, and I want to take the determinant, so I don't want to do that. Determinant of that is set equal to 0. And I'm going to have minus 5 minus lambda 4. 4 minus 5 minus lambda determinant. I have minus 5 minus lambda squared minus 16 is 0. Okay, so I've got 25 plus 10 lambda plus lambda squared minus 16 is 0. I've got lambda squared plus 10 lambda plus 9 is equal to 0. I can factor that. Lambda plus 9, lambda plus 1 is 0. So my lambdas, my eigenvalues are going to be minus 9 and minus 1. All right, so we'll use minus 1 first. So now we're going to look for eigenvectors. Case 1, lambda 1 is equal to minus 1. So I've got minus 4, 4, 4, minus 4 times V1 has to be 0, which implies by inspection V1 is 1, 1. In case 2, lambda 2 is equal to minus 9. And I end up with 4, 4, 4, 4 times V2 is equal to 0, which implies that V2 is equal to 1 minus 1. Okay? Now, lambda is equal to alpha squared, which implies that I have omega 1, which is going to be 1, and omega 2, which is going to be 3. And now I can just write down the answer. I have a real part, x of 1 is equal to a1 cosine t plus a2 sine t plus b1 cosine 3t plus b2 sine 3t. So that's the top guy, that one. and that one are the top guys that are sitting there. Boom, 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 boom. And I've got an imaginary part, x2t, which is going to be a1 cosine t plus a2 sine t minus, because we got a minus sign sitting there, b1 cosine 3t minus b2 sine 3t. And that's my final answer. And lo and behold, it would check in the back of the book. If the back of the book bothered to give you the answer that way, it chooses to use words. Number 4, I have m1 is equal to m2 is equal to 1. I have k1 is equal to 1, k2 is 2, and k3 is 1. Okay, so I've got a matrix M, 1, 0, 0, 1. I've got a matrix K, minus 3, 2, 2, minus 3. Because the identity matrix is its own inverse, my A is minus 3, 2, 2, minus 3. The A of x double prime is equal to AX. That's the A I'm talking about. Okay, we want to find the eigenvalue, so A minus lambda I. Determine that has to equal 0, so I have minus 3 minus lambda, a 2, minus 3 minus lambda, determinant, minus 3 minus lambda squared, minus 4 has to be 0, so I have lambda squared plus 6 lambda plus 5, so I've got 9, 3 squared is 9, minus 4 is 5, has to be 0. So I'm going to factor that. Lambda plus 5, lambda plus 1 is equal to 0. And my lambda values, my eigenvalues, are going to be minus 1 and minus 5. Okay, case 1. Now I got to find eigenvectors. Case 1, lambda 1 equals minus 1. Okay, so I want A minus lambda I times V1. That's what I'm doing. Has to be 0. So I've got minus 2, 2, 2 minus 2 times V1 is 0. And by inspection, we have V1 is equal to 1, 1. Case 2. lambda is equal to minus 5. So I have 2, 2, 2, 2. V2 is 0, implying that V2 is going to equal 1 minus 1. I got that lambda is equal to alpha squared, which implies that omega 1 is going to be 1, and omega 2 is going to be square root of 5. Okay, so now we're going to write down the answer. We have a real part. x1 of t is equal to a1 cosine t plus a2 sine t plus b cosine square root of 5t b1 plus b2 sine square root of 5t and an imaginary part x2t, which is going to be a1 cosine t plus a2 sine t minus b1 cosine square root of 5t minus b2 sine square root of 5t. And that's all there is for number 4. Okay, moving on to number 6. I have M1 is 1, M2 is 2, K1, 2, K2 is equal to K3, which will be a 4. Okay, so I've got an M that is 1, 0, 0, 1, 0, 2, that guy there. And I've got a K that's going to be minus 6, 4, 4, minus 8. Okay, and I need an A. So I need an M inverse. So 1, 0, 0, 2, dividing line 1, 0, 0, 1. I'm going to divide by 2 on the second row. 1, 0, 0, 1. 1, 0, 0, 1 half. So that clearly implies that M inverse is 1, 0, 0, 1 half. And my A is going to be M inverse K. And M inverse K is going to be minus 6, 4, 2, minus 4. So first row 1, first row, first column minus 6. First row, second column 4. Second row, first column a half, 2. First row, second column, a minus 4. Okay, so now I know what my A is. And with my A, I can find eigenvalues. So I want A minus lambda I, and I want to make it equal to 0. Minus 6 minus lambda 4, 2 minus 4 minus lambda, absolute value, equals minus 6 minus lambda minus 4 minus lambda minus 8 is going to be 0. Okay, so it looks like I've got lambda squared plus 10 lambda I've got 24 minus 8, which would be plus 16, is equal to 0, and I can factor that lambda plus 8, lambda plus 2 is equal to 0. So I have eigenvalues minus 2 minus 8. All right, now I need eigenvectors. Case 1. Lambda 1 is equal to minus 2. Okay, so I have minus 4, 4, 2 minus 4 minus 2 times V1 has to be 0, which implies by inspection V1 will be 1, 1. Case 2. Lambda 2 is equal to minus 8. And I have 2, 4, 2, 4 times V2 is supposed to be 0. So by inspection V2 is going to be 2 minus 1. Okay. My eigenvalues are equal to alpha squared, which implies that omega 1 is going to be the square root of 2, and omega 2 is going to be 2, the square root of 2, which is also known as the square root of 8. Okay, so now we can write down our final answers. We have a real part. x1 of t. x1 of t. a1 cosine square root of 2t plus a2 sine square root of 2t plus 2, that 2 right there, plus 2 cosine 2 the square root of 2t plus 2 sine is a b1, b1, b2 sine 2 the square root of 2t. And there's an imaginary part, x to t. A1 cosine square root of 2t, A2 sine square root of 2t, minus b1 cosine 2 the square root of 2t minus b sine 2 square root of 2t. And with that, we are done with section 5.4.